Okay, thanks everyone for coming today. I'd like to welcome you to an EOL seminar. I'm very pleased to introduce Adriana Bailey, who's currently a postdoctoral fellow at Dartmouth. She got her PhD here in Boulder at CU in the ATOC department, working with David Noon, and during that time actually participated in a couple EOL-led field campaigns, both ICE-T, which was based in St. Croix, and then the Ideas 4 campaign on the C-130. She graduated in 2014 and then moved to Seattle, where she did a postdoc with Rob Wood, actually working on satellite data, not airborne campaigns. And in addition to her experience and interest in clouds in the remote part of the atmosphere, she also has a thing for mountains. So she's done work at Storm Peak Lab, at Niwot Ridge, at Mauna Loa, and at Mount Washington on climate change feedbacks and dynamics and complex terrain. So I'm looking forward to her talk, and I won't read your slide, but expecting to get a nice overview of what she's been working on. I guess I should mention that she's an expert in measuring water vapor isotopes and applying that to understanding the water cycle. So with that, thank you, Adriana.
Thank you very much for that introduction. Please let me know if at any time you can't hear me, but I think this is working okay. Yeah, it's funny that you mentioned you'll definitely get a lot of water isotopes in this talk. You'll also see a little bit about mountains, but it's kind of funny. I feel like the reason we end up going to mountains is because we don't have a plane. And so we go to places where we feel like we can get some sort of a vertical profile with much cheaper techniques. But I'm really excited to be here today and to tell you a little bit about my research, which I wanted to give you sort of a little bit of overview of here. I use a variety of instrumental approaches, looking at in situ observations, looking at remote sensing observations, and I'll also pair that with modeling to try to think about water's role in the climate system. And when I think about why water seems so central or important in the climate system, there are really two factors that come to mind for me. One is that it's through the water cycle that I think most of us experience climate variability and also long-term change. And I'll share a couple examples from the places I've most recently lived to give you, to kind of help make the case for that. So after earning my PhD in 2014, I went out to Seattle to work at the University of Washington, and right in time for the 2015 warm and dry winter that was dominated by the blob, which was these very anomalous warm sea surface temperatures in the North Pacific. And the results of the blob are really illustrated here. The ski resorts in Washington simply couldn't stay open that year. Most of them were closed by early February, and also the water reservoirs that feed the city of Seattle were far below normal. Now I'm at Dartmouth College, which is in New Hampshire in the northeastern United States, and there they've also been experiencing some rather dramatic changes in their water cycle. So for example, the northeastern United States is seeing the largest uptick in heavy precipitation of the entire country. And in addition to that, regardless or despite that uptick in heavy precipitation, they're also seeing this increase in severe erosion simply due to the fact that soil conditions are much wetter on average. Now, the second big reason I think the water cycle is so important for climate is that the water cycle and its feedbacks are going to regulate how much the Earth warms in response to climate forcings. And so, for example, we know that globally, the water vapor feedback works to increase the forcing by about 2 watts per meter squared for every degree increase in temperature. And the reason that occurs is that the H2O molecule is an incredibly efficient absorber in the atmosphere, and particularly the long wavelengths, which you can see here. This black shading shows the absorption in the atmosphere, and here's the portion that's being carried out by the water molecule. We also know that saturation vapor pressure of the atmosphere is very dependent on temperature. And so we expect a warmer atmosphere to be a moister atmosphere. But while we have a good sense of how the water vapor feedback works on a global scale, I think there are still some questions about how it works on regional scales. And so an area of my current research that I won't unfortunately talk much about today is that we're looking at how variations in water vapor in low humidity mountain environments might make those mountain environments more susceptible to an accelerated warming. And I'm doing that with collaborators or colleagues at Mount Washington Observatory, which is pictured here. And you can get a little flavor for the instruments that I work with. We set up a pilot project last summer and early fall to take some measurements up there. Water also exerts feedbacks on the climate system in its capacity, or I guess in the form of clouds. But what's different about cloud feedbacks on climate is that we're much less certain about them than we are about the water vapor feedback. And part of that is because clouds have a much weaker direct dependence on temperature, and also because we're still really working to understand what are the mechanisms that control cloudiness. So here's an area of research that I think would be a lot of fun to pursue here as part of the Research Aviation Facility, because I think that there are some key hypotheses that have been posed in recent studies, and I think we can test these hypotheses observationally. For example, thinking about how vertical mixing processes in the lower atmosphere regulate cloudiness and therefore cloud feedbacks on climate. So I'll touch upon this a little later in the talk. But one other thing I wanted to mention is water in its precipitation form. And there isn't a precipitation feedback per se, but I would argue that precipitation will play a role in shaping both water vapor and cloud feedbacks regionally because it's the main sink of water in the atmosphere. It also has the effect of being one of the main scrubbers of pollutants from the atmosphere, and we know that pollutants like aerosols interact with the climate in a variety of direct and indirect ways that we're still really working to understand. Now, the problem with precipitation processes is that they're very hard to observe and model. So for example, the spatiotemporal coverage of our observations is not as dense as we'd like. When we look at satellite records and satellite observations, they don't agree as much as we'd like in capturing long-term trends in precipitation. We know that we have trouble with parameterizations of precipitation processes in our models. And lastly, there's a lot of high natural variability in precipitation systems. And I think these last couple points are nicely illustrated for me by this figure from Shepard 2014, where we're looking at precipitation changes from the CMIP-5 ensemble projections for RCP 8.5. And as you might expect, increases in precipitation are shown in cool colors and decreases are shown in warm colors. But where I really want to draw your attention is to the stippling and to the hatching within this figure. So the stippling suggests where some of these changes are significant and models agree, 90% of models agree. And the hatching shows regions where the natural variability is higher than the projected change. And what I want to draw your attention to is if you look at sort of vast regions here around the globe where we might care about climatically, like the subtropics or even the United States, is that we are not particularly confident in the anthropogenic contribution to precipitation changes in these regions. So for me, these limitations are actually a big motivation for why we would want to develop or identify different frameworks that we can apply to these problems, frameworks that lend new observational tools and perhaps also provide us with some new model parameterization constraints. So the framework that I want to introduce to you today, probably not an unfamiliar one, but we'll give a little isotopic twist to this. And that is thinking about these problems from a water balance lens. And when I think about water balance here, what I'm essentially thinking about is the balance between evaporation and precipitation processes. So I'll give you two applications, one at the regional scale, where we can think about characterizing imbalances in precipitation and evaporation, thinking about how those imbalances will shift or intensify with climate variability and climate change. And I'll also want to show you how this works at a weather system scale, because I think that's where we can start to ask some really exciting questions about how do cloud and convective processes work, how can we improve their parameterizations in models. Now, even though I started, my research timeline really starts on the weather system scale, I'm going to start here today with the regional scale because I think it's a slightly more intuitive level at which to kind of think about this new framework and this new observational application. So at a regional scale, when we think about hydrologic balance, We can think from an atmospheric perspective that evaporation is the main source of moisture to the atmosphere, precipitation is the main sink of moisture, and then because these processes are not often in equilibrium at a given location, we have the atmospheric circulation playing the part of moving moisture from regions of evaporation to regions of precipitation. And we can represent that with the moisture flux divergence. So over on the right, you'll see the equation. What it's showing here is that the change in Q, or water, for a given location over time can be given as a linear combination of evaporation, precipitation, and the vertical integral of the moisture flux divergence, which I'll often denote simply as DIV. Assuming steady state conditions, what we see is that the vertical integral of moisture flux divergence should balance E minus P, so imbalances in evaporation and precipitation. And we can see that when we look at these climatological patterns of both E minus P and divergence from era interim reanalysis. So the top plot is showing E minus P, the bottom plot divergence. And what you'll notice is that in very wet regions, such as across the ITCZ and in the West Pacific warm pool, you see that precipitation dominates, and as a result, divergence is actually negative because we require a convergence of moisture to sustain the high precipitation rates there. Whereas in dry regions like the subtropics, where evaporation dominates, we see that divergence is positive because we're exporting moisture to other regions. Now, as climate changes, we anticipate that these patterns may actually amplify, thus intensifying the hydrological cycle. And this was put forward or described very nicely in a very seminal work by Held and Soden in 2006. And here they're actually giving the fractional change in P minus E, but that's equivalent to the fractional change in E minus P. And what they suggested is that this fractional change simply scales with temperature. And their projections for different zones are shown by this dashed line. And then they have the solid line shows model simulations from GCMs. The key take home of this figure is that wet regions become wetter, like the ITCZ, and dry regions become drier, like the subtropics. And because there's a simple scaling here with temperature, and we know approximately how much temperature has increased globally, we can make predictions that we should already be seeing about a 4%, or probably now going on a 5% increase in intensification of the water cycle. Do we have an observational way of actually validating that or evaluating that prediction? Well, there certainly have been efforts to try using satellite records of precipitation. And here's one example where we're looking at the climatology of precipitation across the tropics in the contours. And then you see projected or estimated increases in precipitation in the colors, where the warm colors are showing possible increases and the cool colors are showing possible decreases. But what we find is that a lot of these estimates depend very strongly on the data product that's being used and also on the time period that's being considered. And the other issue is that these sorts of observational estimates are ignoring the evaporation component of this hydrologic balance. And granted, the evaporation part is smaller in many places, but there are certain locations where I would argue that it's non-negligible. So understanding some of these limitations, there was a group in Australia led by Durack that decided to look and see if they could use salinity measurements to try to come up with an estimate of hydrological intensification. And what they used was this Argo float network that's mapped here. They plotted changes in salinity for different regions by the mean salinity anomaly of those regions. And from that, we're able to back out from these regression lines that the hydrological cycle may be intensifying at double the rate that was predicted by Held and Soden's thermodynamic model. So since then, others have argued that, well, you can't actually necessarily make this assumption that salinity is simply reflecting more precipitation or more evaporation over ocean regions. In other words, just because it rains more doesn't necessarily mean it will be fresher, because there's a lot of oceanic mixing going on as well. So we're still left with not exactly a clear answer to whether we can track hydrological changes and think about how these imbalances in E minus P may be shifting or amplifying. So that's where this new framework and a new observational approach comes in. And the observational tool by which I'm going to think about this problem from a hydrologic balance is isotope ratios in water, because they actually give us a way to track the balance between evaporation and precipitation. So up top here, I have the water molecule that we all know very well, H2O. But here are some others that I know I think about on a day-to-day basis, but I'm not sure everyone else does. Here are heavy isotopologues of water with either a heavy oxygen or a heavy hydrogen. And for analytical purposes, what we tend to be interested in is the ratio of a heavy atom to light atom for a given element. And then we often express these isotope ratios relative to a standard such as ocean water to derive what's called delta notation. So I may say isotope ratio throughout this talk. You may also hear me say delta O18 or delta D, which is simply referring to those isotope ratios relative to their standards. Now, the reason that isotope ratios work as good tracers of hydrologic balance is that they experience different saturation vapor pressures. And so the heavier isotopes or isotopologues are more likely to condense and rain out, while the lighter ones are more likely to evaporate. And so as we see evaporation processes, the atmosphere becomes lighter and lighter, but as condensation and precipitation occur, we see the atmosphere. I should say that was actually the opposite. As we see condensation processes that take the heavy ones away, the atmosphere becomes lighter and lighter. And so there are some simple isotopic models that we can think about, or some simple ways of viewing the tropics and the subtropics that help support this idea or give us sort of the theoretical foundation we need to think about why isotopes might be good tracers of evaporation and precipitation and imbalances in those two fluxes. So let's imagine that we're in the deep tropics, and we assume that moisture in this region is going to become depleted with height in the atmosphere through precipitation following a pseudoadiabatic process. So we sort of make the assumption that it's generally most of the condensate that forms rains out. Isotopically then, our isotope ratios, our delta D, is going to follow this Rayleigh distillation, where this is the way that the isotope changes as a function of the water vapor volume mixing ratio. Now in contrast, if we come to a region like the subtropics, where we have much less deep convective development, more shallow convective mixing, we might assume that the vertical profile of moisture in the atmosphere is better described by a mixing process. In essence, it's a mixing process that actually transports moisture in the vertical. If we model the isotopes following this pattern, then what we generate is this solid blue line. And so you can see that for a given water vapor volume mixing ratio, the isotope ratio is more enriched in a mixing or evaporative environment, and the isotope ratio is more depleted in a precipitating environment. And so essentially what we need to be able to capture this in either models or observations is we need vertical profiles of the water vapor volume mixing ratio and the isotope ratio to be able to generate or to sort of estimate the isotope ratio for a fixed Q. So we need delta D at a fixed Q, which I will refer to as delta DQ. So let's take a look at how this metric performs. So here are climatological patterns of divergence, which is our estimate of E minus P, and then also delta DQ in CAM5. And this is an isotopically enabled version of CAM5. So here up top, again, you see the pattern of negative divergence in regions where precipitation dominates and positive divergence in regions where evaporation dominates. And then for delta DQ, what we see is the delta DQ is much more negative in those regions where precipitation dominates and much less negative in the regions where evaporation dominates. So really nice spatial coherence. Now I want to show to you that really isolating the isotopic variability independent of water is really key to sort of making this or applying this tool. And so here's what CAM would look like if we had simply plotted the isotope ratio at a fixed height. And we lose that really nice pattern. Okay, the question though is, do we have an observational constraint that can tell us how regional moisture imbalances might shift with climate variability or long-term change? And so we need an observation and we need some climate perturbation. For the observation, we can use these retrievals of both HDO and H2O from the tropospheric emission spectrometer, also known as TESS, which flies here where the arrow is pointing aboard Aura, which is on part of the NASA A-Train satellite constellation. And since our record only goes back to 2004, an obvious choice for our climate perturbation is then El Nino Southern Oscillation, or ENSO. So you'll see that over the course of the most robust period of the satellite record, which is this area shaded in blue over this time series of the multivariate ENSO index, that there are 2 moderate El Ninos and 2 moderate La Ninas. So I'll be showing you composite differences between the La Nina phases and the El Nino phases to think about how regional imbalances in moisture are changing and how we can detect that isotopically. So let's start with these composite different patterns of temperature, cloud top pressure, and also moisture flux divergence. The top left panel here is from era interim reanalysis, and of course, because we're doing this La Nina minus El Nino, that big tongue where you expect really warm water is of course cold and blue. But what you see over here with MODIS cloud top pressure is that the convective reorganization is a little bit different. So over the warm pool during La Nina, we see much higher clouds because we see much deeper convection developing in this region. We also see slightly higher clouds near Hawaii and then over in the East Pacific. When we look at what moisture flux divergence is doing, both in CAM and in the era interim reanalysis, we see that these spatial patterns are very coherent with this large-scale reorganization of convection. So does delta DQ then track this? Here's CAM divergence again, and here's delta DQ in both CAM and then also in the satellite record with TESS down here. And you can see that again, there's very nice spatial coherence. The TESS data, of course, give us a lot more noise, and that's because we only have this pretty short record of 8 years. The satellite only flies over several times, a week perhaps per location. We actually have to filter out a lot of the data as well because TESS is sensitive to clouds, which is a little problematic for this problem that I'm trying to attack. So you can imagine where it would be very valuable to actually get in there and take vertical profiles that don't have these constraints that remote sensing does. But for the purposes of this study, at least let me show you that we've considered some of these sensitivity problems that we might be having, particularly the fact that we're filtering out a lot of the really heavy cloud situations. And what we find is that even when we look at the time periods where TESS is in low cloud conditions, we're still getting the cloud signal, the convection signal that we expect for differences between La Nina and El Nino. Now, I want to talk a little bit then about how we could use this tool as a way to think about intensification of the hydrological cycle, not just detecting shifting patterns with climate variability. And this is work that's still in progress, so some of this is a little bit of a thought experiment. But I thought it would be valuable to share with you because it gives you a sense of how I think about these problems. So I'm going to use the CAM data, and we're going to take the spatial dependence of the changes in delta DQ between La Nina and El Nino and regress them on the spatial patterns of divergence, so the composite difference patterns of divergence, to understand what is the sensitivity of delta DQ to these changes in moisture imbalances. And we derived the slope of about 7 per mil per millimeters per day. Now, here's the thought experiment. We can take some of those precipitation trend estimates that were provided by satellite in previous studies and think that, okay, the change in precipitation over the last few decades is probably something on the order of 0.1 to 0.5 millimeters per day per decade in many regions. And for the most part, changes in precipitation are going to be balanced by divergence because that's the larger aspect of evaporation. Again, it's a thought experiment, so we're making some big simplifications here. So if we then scale this by our slope, we come up with the possible change in delta D in per mil per decade. And then if we have a long enough record, several decades, we'd see a 4 to 20 per mil change in delta DQ. Now that's not something that we could detect by the satellite in its current state, but it certainly is something that we could detect with water vapor in situ isotopic analyzers. And what's exciting is that right now NEON, which is just down the street, is actually deploying water vapor isotopic analyzers at terrestrial sites across the United States for the next 30 years. So we really have the potential to answer these kinds of questions. But that's 30 years in the future, and we kind of want to know what's going on now. We certainly don't have 60 years of water vapor data going into the past, not at any site, let alone at a vast network. What we do have are precipitation isotope records going back 60 years. This is the global network of isotopes in precipitation, and I realize that this particular figure is a little fuzzy, but the reason I like it is that it sort of shapes these dots. The bigger dots suggest that more data has been taken over more time. So you can get a sense for the representativeness of how long these records have been going on. And so using this kind of a record, we could take areas like the subtropics in the North Pacific, bin the data together, remove the station means, remove the monthly means, and come up with an estimate of delta D change over a long time period. But is there the same connection between the delta D of precipitation and also moisture imbalances? The answer is there is. So here are the composite differences between La Nina and El Nino for CAM, delta DQ. And on the bottom, what you'll see is the changes in the delta D of precipitation. So the dependence is a little weaker, but it's the same spatial coherence. And so if we redo our thought experiment using the slightly different dependence of delta D on divergence, it suggests that we should be seeing a 1 to 6 per mil change in the precipitation isotope ratios. And that, again, is something that we can certainly observe. So this is very preliminary, but here are the mean changes in delta D for different regions according to the GNIP record. So this is the precipitation isotope ratio record. And what really stands out is that the significant changes are occurring in the subtropics, where we're seeing increasing isotope ratios consistent with the amplification of E minus P and intensification of the hydrological cycle. And the largest of these are actually in regions where we have the hardest time using traditional precipitation metrics of estimating the change in hydrological intensity. So I think that's really the value in bringing kind of this new or just a different framework to the problem, where you can have a new observational tool, is you now have this opportunity to answer questions that in places where traditional metrics just don't have the same kind of power. Another advantage in particular of using water isotope ratios is that they have this really nice connection to past climate. So if we think about wanting to link changes in current climate with changes in past hydroclimate, we can do so a little bit more directly, given the fact that we base our interpretation on past climate off isotopic proxy records from things like speleothems and tropical glaciers. And I know there's quite a bit of work here at NCAR to kind of explore some of these changes in past climate to really understand the future. And it would be great to be able to partner in some sense with those groups as well, if that were an opportunity. Okay, so we've looked at this at the regional scale. Let's bring this to the weather scale and start to talk about some questions that are particularly important for understanding clouds and convective processes in models. So in many senses, we'll be applying the same type of evaporation and precipitation framework. And the way to think about it, or the way that I think about this, is that a lot of questions revolve around this notion of, are clouds precipitating or are clouds evaporating? And so one of the papers that really struck me a few years ago was a 2014 paper by Steve Sherwood and colleagues that came out in Nature. And they really talked about the importance of precipitation versus evaporation in shallow convective environments. They argued that if these shallow convective clouds are tending to evaporate more than precipitate, that they're moistening the free troposphere at the expense of the boundary layer, and essentially reducing the precipitation efficiency of the region. They called this whole notion lower tropospheric mixing, kind of like a cloud mixing term, if you will. And they went as far as to suggest that not only is this going to have implications for how things are transported through the hydrological cycle, such as moisture, other atmospheric constituents, but that it may actually be what describes the differences in climate sensitivity among GCMs. In other words, models that have more of this lower tropospheric mixing, where clouds are evaporating instead of precipitating, have a higher climate sensitivity, meaning a higher predicted temperature for a given amount of CO2. Right, but in this particular paper, there wasn't a particularly strong observational constraint from the regions where shallow convective processes are really strong. And so I think we have opportunities to characterize the precipitation efficiency of convective systems, to think about how that transports or changes the transport of moisture in the atmosphere, how it changes the transport of other constituents important for climate, like aerosols, and then how it possibly influences cloudiness and perhaps low-level cloud feedbacks on climate. So how do we take our water balance lens to this problem? Well, remember that before, what I suggested to you is that if you can isolate the isotopic variability independent of changes in humidity, that you can distinguish evaporation from precipitation-dominated environments. There's no reason that we can't apply that or take that from sort of a regional scale and then say, let's look at precipitation versus evaporation-dominated cloud systems, where we expect that the more precipitation-dominated systems will be precipitation efficient, probably deeper convection, and that the more inefficient systems, the ones that are evaporation dominated, will be dominated more by shallow convective mixing. There's a mathematical theory to underpin why we might apply this framework in this manner. And what I'd like you to keep in mind is the Rayleigh process, which I mentioned briefly earlier. So recall that if we assume that a cloud system is essentially following a pseudo-adiabat, and all moisture that condenses is immediately removed, then the isotope ratios are going to follow what's called this Rayleigh distillation. And by definition, that has to have a precipitation efficiency of 1. So here's how we actually model Rayleigh distillation. We have our isotope ratio as a function of the isotope ratio at a reference level, the fractional change in humidity, and then the small dependence on temperature through this exponent. And again, this assumes that we have a precipitation efficiency of 1 by definition. We can modify this model to include this precipitation efficiency term, and which I've denoted E here, but I often refer to as PE for precipitation efficiency. And the take home of this big equation is that when the precipitation efficiency decreases, the isotope ratio increases for a given water vapor volume mixing ratio. So you expect less depletion in your isotope ratios if your precipitation efficiency is lower. So equipped with this framework, how can we think about characterizing the precipitation efficiency of convective systems and using that to answer questions about what actually drives different precipitation efficiencies and how does that impact atmospheric constituents like aerosols and trace gases? So we went to the Mauna Loa Observatory to set up a multi-year campaign to answer this question. And the instrumentation we used was, at the time, this pretty brand new water vapor isotopic analyzer that is now being produced, I don't want to say mass produced, but now being produced in the hundreds by Picaro. So there are a lot of behind the scene things that go on in using these isotopic measurements. And we've had to think a lot about what are the right inlets to use, what are the right calibration strategies, also how do you post-process the data to take out certain biases. So that's all encapsulated in some manuscripts that are either published or in prep. And if anyone's interested, I'm happy to talk a little bit more about that afterwards. But for now, suffice it to say that despite issues with this measurement system, it's actually quite impressive what it can do. So there were a couple of reasons that we went to Mauna Loa, as we thought that it was a really ideal place to think about how you could get a vertical profile in a place where you might not have an aircraft. So Mauna Loa is located at 3,400 meters above sea level, basically in the middle of the Pacific. Most of the time, at least at night, it's situated in the dry free troposphere, and you can really get a sense of that from this very xeric and sparse vegetation at the higher elevations compared to what you see down below near the seashore. But there's also very strong convective growth and convective boundary layer development during the day. So as that occurs, what we see is a lot of the moisture and the constituents in the boundary layer actually reach the observatory or surpass it. And that gives us an opportunity to sample a vertical swath of the atmosphere, again, without the support of an aircraft program. Mauna Loa is also a nice place because there's kind of a steady stream of constituents like aerosols into the boundary layer because of the active volcanism on the island. So to give you a sense of what you'd see if you were actually making measurements at Mauna Loa Observatory, this is a composite plot of a diurnal cycle for the time period that we were up there measuring. And these are for some of the strongest convective days that we actually saw. And what I plotted here are the average diurnal cycles for water vapor volume mixing ratio in blue, and also the aerosol condensation nuclei concentrations in black. So essentially the aerosol concentrations. So to characterize precipitation efficiency in this environment, I gave you a bunch of mathematical formulas that you could use to do this, but I actually took a statistical approach. So for each day that we were out there observing, I asked, okay, for the peak humidity that we see, what does the isotopic ratio look like? In other words, is it more enriched than we expect? Is it more depleted than we expect? And based on those anomalies, I characterized these low precipitation efficiency and high precipitation efficiency regimes. And I only did this for days in which moisture passed a certain threshold, which is given by the dashed line here, because I wanted to look at days in which convective growth is strong enough that some boundary layer air actually does reach the observatory. Although this was done in a statistical fashion, you can see that it aligns actually very nicely with our predictions. This graph is actually underlain, it underlies here. This is the solid line shown here, the Rayleigh distillation, which by definition has a precipitation efficiency of 1, but it's a little hard to see this dashed curve, but there it is. So what do we learn about convective systems when we're able to characterize them by their precipitation efficiency? We learned that there are multiple dynamical drivers of strong convection in the subtropics in a place like Hawaii. So when we look at anomalies, for example, in the zonal winds at the jet level, when we have low precipitation efficiency near Hawaii, we see the strengthening and bending of the jet stream. And this westward retraction actually creates a jet exit region, and also juxtaposed against the easterly trade winds enhances wind shear. So you have these two conditions, both of which are very conducive to convective activity. But this jet is also bringing air that's from a higher altitude and also a higher latitude, so probably much drier than what you'd see in the subtropics. And that juxtaposition of dry air on top of moist air is probably what causes these low clouds to evaporate as they're convectively developing, rather than allowing them to really develop and precipitate. In contrast, when we have high precipitation efficiency conditions, we don't see a lot of anomalous activity at the jet level. Instead, what we see at the surface is that there's a weakening of the high pressure system, usually the subtropical high that sits over Hawaii, which allows more meridional moisture to come up from the tropics. And so you can really see how these different circulation pathways also how this affects the transport of air masses to this region. So these are some high split 3-day back trajectories for low precipitation efficiency conditions and high precipitation efficiency conditions. And when we have low conditions, we see much more air coming from the west, the northwest, the Eurasian continent. And when we have low or high conditions, much more of that air is coming from right around Hawaii and to the south. And it turns out that this has a big impact on certain atmospheric constituents that we care about for climate. So here are the composite diurnal cycles in ozone measured at Mauna Loa Observatory for high and low precipitation efficiency conditions. And what you can see is that based on where these air masses are coming from, we have very distinct background conditions, with the higher concentrations associated with this Eurasian air and the lower concentrations associated with this cleaner tropical air. There are also differences in the diurnal variability of these concentrations. But what the solid line underneath these data points is showing is a vertical mixing model. And you can see that the model aligns quite nicely with the data. And that suggests to us that we can actually characterize the differences in diurnal variability based on differences in vertical mixing. So all in all, it's the dynamics, whether it's the large-scale flow or the vertical mixing, that's really controlling the concentrations and the variability in ozone between these different precipitation efficiency conditions. The story is very different when we look at aerosols. So to start, if we look at the background conditions of aerosols, we realize that there's really no difference. And so that suggests that different emissions from Eurasia or from tropical regions are not really characterizing the background aerosol that we see. Instead, where we notice differences is towards the middle of the day, particularly during high precipitation efficiency conditions. You can see that the observations begin to drop off much more quickly than the vertical mixing model predicts. And that suggests to us that there's a scavenging of aerosol that can't be explained just by air mass motion. If you look at the composite diurnal patterns in precipitation at Mauna Loa, you'll see that that's right about the right time period when precipitation really starts to kick off. So evidence for precipitation scavenging of these pollutants. Later in the day, you actually see that the aerosol concentrations during high precipitation efficiency conditions are higher than expected. And so our speculation here is that as you scavenge some of those big existing aerosols, you're kind of opening up an area for new aerosols to form, in other words, to nucleate or to form particles. And so as those particles then drift back down to Mauna Loa, you observe these higher than expected concentrations. And there's additional evidence for that when we look at a component like the angstrom exponent, which is basically telling us about the differential scattering at different wavelengths for these aerosols. When we have high precipitation efficiency conditions shown here in red, the angstrom exponent is larger. That means that these aerosols are preferentially scattering smaller wavelengths, and that's indicative that these are also smaller particles. And we would expect smaller particles if we have nucleation occurring. So in essence, a little cartoon to summarize, when we have low precipitation efficiency conditions, we see this strengthening of the jet stream, which brings very dry air to Mauna Loa, which then basically mixes with the moist marine boundary layer air, causing those low-level or shallow convective clouds to evaporate. In contrast, when tropical plumes cross the island, we see much more convective development, greater precipitation efficiency. That precipitation scavenges aerosols from the atmosphere, reducing the condensation sink for sulfuric acid vapors, which can then create new particle nucleation. As a little teaser, I've started looking at some of these connections between precipitation efficiency and precipitation scavenging outside of the tropics, here actually in the Northeast, in a mid-latitude climate. And what we're starting to see is, again, some really nice correlations between how the isotope ratios indicate that the precipitation efficiency of these convective systems or rain or weather systems have changed, and what the chemistry is in those systems. So there's actually another paleoclimate kind of implication for this work, if you will. That is that if you can imagine you're sitting there with an ice core record of isotopes and also pollution concentrations, a key question you might have is, well, is this record telling me that pollution has changed because the transport pathway has changed? We're getting stuff from different source regions? Or is it because the hydrological cycle has changed and we're actually seeing more rain out along the pathway? And the evidence that we've gathered from Hawaii and that we're starting to gather from Mount Washington are suggesting that the precipitation processes are very important. But back to the question at hand. So we've been able to characterize precipitation efficiency to learn something about how large-scale dynamics control the balance of precipitation and evaporation in weather systems, and then to see the effects that that has on moisture transport and also on the transport of pollutants like ozone and aerosols were the two examples I gave. But I also left you with this idea that maybe if we can characterize precipitation efficiency, we can also start to understand the connections to low-level cloudiness, macroscopical or macrophysical properties like cloud lifetime and cloud fraction, which may give us an indication of how cloud climate feedbacks will play out in the future. So can we answer Sherwood's idea that maybe if low clouds evaporate more frequently rather than precipitating, if they have higher lower tropospheric mixing, does that mean we also have larger cloud climate feedbacks? I think we can answer this, right? The Mauna Loa experiment told us that large-scale dynamics is the first-order control on precipitation efficiency. If you're not distinguishing between, kind of what's going on in the large-scale environment, that's going to be the first-order control. And so if you want to understand the variability in precipitation efficiency for a particular dynamical regime, I think we need repeated measurements under very similar large-scale conditions. Once we have those measurements, we can start to pair them with, say, active remote sensing of some of those cloud properties that I mentioned, like cloud lifetime and cloud fraction. Now, we also know that to be able to characterize the precipitation efficiency of these systems, we want vertical profiles of both moisture, and we want high-resolution vertical profiles of isotope ratios. And so when we did this, or tried to do this with, again, our very cheap platform, putting our instrument in a truck and trying to profile the vertical around Hawaii, what we realized is that with a very high resolution profile of both moisture and isotope ratios in moisture, you can actually back out changes in the precipitation efficiency within a single vertical profile. So imagine what we could do if we had a plane. Thanks so much. I'm happy to take any questions.
Thank you, Adriana. So we'll use the microphone for people who are online.
You were listing what the precipitation was, but I didn't actually catch if this was surface measurements in Hawaii, in which case they probably vary around the island depending on the large-scale flow, or if it was satellite measurements over a much larger area.
Oh, right. So these were actually taken with that box, the Picaro that I showed you, that was sitting at the Mauna Loa Observatory using the aerosol stack. So we were basically sampling off the same air from which a lot of the Mauna Loa baseline measurements come in.
Chris?
So I might be off base here, but it seems like one of the feedbacks that would be very sensitive to mixing is the albedo feedback from low clouds. The more mixing, you may just eliminate these clouds in the climate model, and you don't have that feedback available. So does your methodology tell us something about that, or is this separate from what you're considering?
Well, and in that sense, were you thinking about, basically the coverage of the clouds, the fraction?
Yes.
So that's exactly what I was thinking about.
That's
right.
that's contained in here in terms of you're able to understand cloud fraction through this.
Not through the precipitation isotope ratios. Okay. You would definitely need to have some sort of I would suggest an active remote sensing measurement, radar, LiDAR on a plane that could actually give you the clouds, a radar. Yeah. Yeah. What the isotopes will tell you is something a little bit more about, they give you a sense of actually the rainout history of these clouds. So the extent to which they've evaporated, the extent to which they've precipitated, and then you can pair that in very nice ways with radar estimates of the aging of the clouds as well.
Adriana, can you say a little bit more about how say you had a scatter plot of delta D versus Q, how you derive the delta DQ from actual measurements?
Right. So what you really need are vertical profiles. So you can imagine that if you have a vertical profile of humidity, and then you also have a vertical profile of delta D, or you really want the HDO concentration, but that's easy enough to derive, you would estimate or sort of think about, you can regress the two together to basically predict what the delta D should be at a particular volume mixing ratio that you're interested in. So I had done some sensitivity work as part of my PhD, which suggested that 4 is a very good number for the satellite observations from TESS. And so that was the number that we went with. But there's a little bit of arbitrariness there in terms of which volume mixing ratio it could be. And I think that the Mauna Loa measurements show that, because there we were able to consider a whole range of volume mixing ratios from about 7 up until 20,000, 7,000 to 20,000 ppmv, over which we were able to characterize the precipitation efficiency.
Other question in back. Hang on a second.
I might have missed something along the way, but I have a very hard time understanding what precipitation efficiency as a function of height means physically. Yeah,
so in that one example I showed you, this was a case where a cloud had actually evaporated here in this region. And so there was a moistening then of the water vapor, the moistening of the atmosphere, which we were then able to detect isotopically.
Yeah, I understand that, but what does that have to do with precipitation?
Perhaps I'm not, so if the cloud evaporates rather than precipitates, the moisture is being kind of contributed back to the atmosphere rather than being recycled back towards the surface or back through the boundary layer.
So you're looking at a range of different heights of shallow cumulus? Is that what the height variable means?
Yes, I think you could. I think, to first order, what you would want to do is find out for a profile within a shallow convective environment or shallow cumulative environment, what is the best model to fit it? And then I think you start with sort of one estimate of what is the precipitation efficiency of that system rather than thinking about precipitation efficiency by height. But part of the reason for showing this is that I wanted to suggest to you that we have the sensitivity to distinguish between these precipitation efficiency estimates with existing instrumentation.
I'm sorry.
So you were mentioning that sea surface obviously is one source, and you were mentioning that that was like a constant value. But how constant is it really over the globe? And when I look at profile like this here, does the air that you see between, say, 800 meters and 2 kilometers, is that long distance transport? What you have up at 2,000 to 2,300 is a recent anvil and so on. And do those, if that's the case, are there ocean variabilities in these ratios that actually play a role in this as well?
So yeah, these are really good questions, and I've actually thought quite a bit about them. In terms of the variability, the ocean surface water itself doesn't vary very much isotopically. Certainly you can have different evaporative regimes which could affect the isotope ratio of your evaporative flux. We had done some sensitivity tests with the test data that I showed, the satellite data, that suggested that given the sea surface variations that you see with El Nino, those variations should not actually cause a very large change in the isotope ratios. And those are big sea surface temperature variations. So for certain questions, you wouldn't want to ignore it, but for the questions I'm talking about, it's probably safe to do so. But it sort of brings up this larger question about, okay, but can you really just treat this as sort of this column that's not really connected to the rest of the atmosphere? And in many senses, we often need to simplify our problems and make certain assumptions like that. But I think you want to check that with a lot of other measurements to make sure that that's an okay assumption to make. And so in this case, what you'd be looking for, are we seeing, for example, a dry air intrusion or something that's kind of coming in from another environment that we need to be aware of? And that's really where I remember aircraft campaigns being so valuable, is that you could get information, say, around a cloud system and really understand what was happening in the broader environment. To understand, okay, well, is this level just something that's like happening everywhere because there's this air mass coming in? Or is this something that's actually related to the cloud processes right here locally?
Okay, thank you. Please join me in thanking the speaker again.